Hi, thanks for joining me. Today I've got a fun number theory problem. We have Sn defined to be the sum from r equals 1 to n of r factorial. So S1 is just 1 factorial, S2 is 1 factorial plus 2 factorial, which is 1 plus 2, which is 3. S3 is 1 factorial plus 2 factorial plus 3 factorial, which is 1 plus 2 plus 6, which is 9, and so on. We want to know for which natural number n is Sn a perfect square. Okay, so S1 is 1, so that's a perfect square. And S3 is 9, that's a perfect square, but S2 is 3, and 3 isn't a perfect square. So certainly S1 and S2 are perfect squares, but what other n are there such that Sn is a perfect square? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. So in fact the solution to this problem is there are only two n for which Sn is a perfect square, namely S1 and S3. So when n is 1 and n is 3, S1 is 1, S3 is 9, both of them are perfect squares. But for any other n, Sn is not a perfect square. And let's see why. Firstly, S4, is you can work out for yourself, is 33, and that's not a perfect square. And then I claim for all n bigger than S4, they sort of share a similar property, which means that it can't be a perfect square. Okay, and what we're going to do is consider numbers modulo 10. So every natural number n is either a multiple of 10, one more than a multiple of 10, 2 more than a multiple of 10, 3 more than a multiple of 10, and so on, up to 9 more than a multiple of 10. In other words, every natural number is congruent to either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 mod 10. And what we're going to do is consider each of those 10 cases, then we're going to square those numbers and look at those numbers mod 10 and see that each of them have a particular property. So let me write that up on the whiteboard. Okay, so I've written a little table on the whiteboard. In the left column we have t mod 10. So remember, every natural number t is either 0, 1, 2, 3, 4, 5, 6, 7, 8 or 9 mod 10. And in the next column I've just written t squared mod 10. Okay, so we have 0, 0 squared is obviously 0, which is 0 mod 10. 1 squared is 1, which is 1 mod 10. 2 squared is 4, 3 squared is 9. 4 squared is 16, which is 6 mod 10. It has a remainder 6 when you divide it by 10. 5 squared is 25, which is 5 mod 10. 6 squared is 36, which is 6 mod 10. 7 squared is 49, which gives us 9 mod 10. 8 squared is 64, which is 4 mod 10. And 9 squared is 81, which is 1 mod 10. Now, I guess the one thing to notice is that none of these numbers in this column here is 3. Okay, none of them are 7, none of them are 8, but in particular none of them are 3. And this is why it's important. If we recall, we have that S4 is equal to 33. But now S5 is precisely 5 factorial plus S4, which is 5 factorial plus 33. Now 5 factorial has a 5 in it and a 2 in its product, so this thing here is going to be divisible by 10. So when I look at it mod 10, this number here is going to be congruent to 33 mod 10, which is obviously the same thing as 3 mod 10. Okay, but because there's no 3 in this column here, there's no natural number which when you square it, you're going to get S5. Because if you would, then 3 would certainly have to appear in this column here. Okay, and the same argument holds for S6. S6 is 6 factorial plus 5 factorial plus 33, which is congruent to, now again, 5 factorial has a 5 and the 2 in its product, but 6 factorial is simply 6 times 5 factorial, so it still also has the 5 and the 2 in its product. So this thing here is a multiple of 10, this thing here is a multiple of 10, so all in all this is congruent to 3 mod 10 again. So S6 is not a perfect square, but you can apply this argument to S7, S8 and Sn, where n is any natural number bigger than or equal to 5. Okay, so then that means that if n is bigger than or equal to 5, Sn is never a perfect square. So we only need to check the first 4 cases, S1, S2, S3 and S4, and we just do that by hand. We know what S1 is, it's 1, S2 is 3, S3 is 9, and S4 is 33. And the only 2 square numbers there are n equals 1, or sorry, in the case n equals 1 and n equals 3, when we have S1 and S3, so 1 and 9. Okay, so there are only 2 perfect squares, there are only 2 n's for which Sn is a perfect square, namely n equals 1 and n equals 3. Okay, I hope you have enjoyed this problem and the solution. If you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. But that's all for today. I'll catch you in the next one. Have a great day.